Okay. Our next speaker is Professor Zhou Jian from Tsinghua University, who's mainly focusing on the study of Gromov-Witten theory, mirror symmetry, and related mathematical physics. So today he's going to talk about Gromov-Witten theory and statistical physics. Yeah, please go ahead.
Okay. Thank you. So it's a great honor and pleasure to be here. I'd like first to thank the organizers for the invitation. This is the plan of my talk. I'd like to discuss the following two problems. What can be said about Gromov-Witten theory from the point of view of statistical physics, and what can be said about statistical physics from the point of view of Gromov-Witten theory. So these two things originally, I think that they're remote from each other. And what I am going to say today probably are just crazy ideas. But I think we need crazy ideas to work on sometimes. So Gromov-Witten theory is the mathematical theory of topological string theory. It is the mathematical version of so-called topological sigma models coupled with 2D topological gravity. In the previous talk, there was an introduction about topological quantum field theory that was obtained by twisting n equals 2 supersymmetric field series, supersymmetric series. But in mathematics, it's based on algebraic geometry or symplectic geometry. So in Gromov-Witten theory, actually, in the mathematical literature, many terminologies in statistical physics has already been widely used, such as partition functions, free energy, correlation functions, specific heat, etc. Their usage in the mathematical literature actually are mainly due to the fact that the mathematicians are following their usage in the string theory literature. So for many of us, we actually don't know what they really mean. Why do we call them partition functions or free energy? I think most of us are in this situation. So I'd like to explain today the following notions in statistical physics actually also useful in Gromov-Witten theory. Something like mean field theory, order parameters, Landau-Ginzburg theory, phase transition, critical exponents, and furthermore, Wilson's renormalization theory and emergent phenomena. The usage of such physical terminology and notions turn out to be lead to some, I think, some bridges between statistical physics and Gromov-Witten theory. So let me recall two paradigms in Gromov-Witten theory. So in this theory, there are two famous kinds of results that provide the paradigms for its study. The first is Witten conjecture conservation theorem. It says that the partition function of the Gromov-Witten theory of a point, the target space is just a point, then it's actually also very interesting. The underlying thing is called the Witten conservation tau function. It's a tau function of a sequence of partial differential equations called KdV hierarchy. And the solution is specified by the so-called Virasoro constraint. There are a sequence of differential operators acting on the tau function to make it zero. So another paradigm is the mirror symmetry for Calabi-Yau threefolds. The target space are Calabi-Yau threefolds. And the Gromov-Witten theory is the type 2A theory. It's a mathematical version of the type 2A theory on Calabi-Yau threefolds. The mirror symmetry says that there's another, it can be identified with the partition function of the B theory on its mirror manifolds. So the A equals 2 supersymmetry has two kinds of twists, A twist and B twist, and they give the A theory and the B theory. And these are for compact Calabi-Yau threefolds, and there are also some non-compact ones which are also interesting. These are the so-called toric Calabi-Yau threefolds, which has a lot of symmetry. So for the compact ones, they do not have much symmetry, but the toric ones has a lot of symmetry. And in this situation, there is another way to do the mirror symmetry in all genera. It says that the partition function of the Gromov-Witten series of a toric Calabi triple can be identified with the partition function of its local mirror curve, defined by something called the Anna-Orenthal topological recursion, which I will recall later. So I'd like to propose to unify these two paradigms based on what I call emergent geometry of KP hierarchy or multi-component KP hierarchy. So I'd like to somehow give some evidence why this is possible. So this proposal is based on some attempts to understand Gromov-Witten theory from the point of view of statistical physics. So let me recall the mathematical definition of the Gromov-Witten theory of a point. In physics, it's just Witten's 2D topological gravity. In other words, it is just the intersection theory on the Riemann-Manifold moduli spaces of stable algebraic curves, which I will not recall. So it parameterizes algebraic curves with mark points, n mark points. At each mark point, we can associate its cotangent space. So we get n cotangent line bundles, and we can consider their first term classes, and these are the observables. And the intersection numbers are just the integral of these classes on the moduli space. And these are called the endpoint correlators in Venus T. So in the previous talk, I think Professor Yu talked about correlation functions, and these are just an example. And as usually in quantum field theory, people consider the so-called generating function by introducing the coupling constant to these observables. So one has to introduce infinitely many coupling constants and form certain formal power series. And this formal power series is called the free energy of the series. And the partition function is defined by taking its exponential, and that's just ordinary standard practice in quantum physics. But in mathematics, since we are dealing with infinitely many coupling constants, we are actually in a situation very similar to statistical physics. We can no longer, in the beginning, consider the convergence of the series and analytic properties of these formal power series. But in this situation, we are in a situation of a topological theory, and it has certain properties which enable us to get to something which is finite. So in the early 90s, in the beginning of this story, Diagraph and Witten studied this Gromov-Witten theory from the point of view of mean field theory in statistical physics. So let me briefly recall what I understand about mean field theory. So for the physicists in the audience can correct me if I make any mistakes, if I made it wrong. So for a system with very large or infinite degrees of freedom, we actually can look for finitely many parameters called the order parameters. So the finite many is important. And also look for a function in these parameters called the Landau-Ginzburg potential. So that the critical point of the system actually are given by the critical point of the Landau-Ginzburg potential. So the critical point actually was a physical notion, I think, when in physics, but also there is a notion of critical point in mathematics. That's just the partial derivative of the potential of vanishing. The blue critical point of the system are physical and these are mathematical. So at the critical point, physical quantities exhibit some kind of scaling properties given by the so-called critical exponents. So when the critical exponents are fractional numbers, one sees the fractional structures. So at the critical points when we actually encounter certain fractional structures. So let me recall how Witten and the diagram proceed. So it's actually based on algebraic geometry. Using algebraic geometry, we can derive certain recursion relations for the correlators when one of them is tau 0. That's called the puncture operator. And then he found that we can remove the puncture operator by reducing these indices by 1 for each one of them. And also in genus 0, there's something very special called the topological recursion relation in genus 0. And based on something like this, diagram, and we can took the other parameters to be the specific heat in genus 0. The specific heat in this case is just the derivative of F0 which respect to T0 second derivative. So U0 is just the specific heat defined in this way. And they derive from the topological recursion relation in genus 0 the following relations. They call it the constitutive relations. The second derivative of F0, which respect to the coupling constant, can all be written as a polynomial in this specific heat. So even though these guys are formal power series in infinitely many coupling constant, but in this specific heat, it's just a polynomial. It's an amazingly simple thing. And in genus 0, the puncture equation actually can be rewritten as a differential equation in this way. And then they take derivative of tau T0 on both sides. Then what they got equation of this form. So this is equation of U0 in terms of this coupling constant. And this is the string equation discovered actually in a setting of matrix model theory. There is a matrix model approach to 2D gravity, and this was discovered in that setting. But using algebraic geometry, they can be re-derived here in this way. So this equation actually determines the U0 as a formal power series uniquely and completely. So the next thing that one can do is to interpret this equation as just the critical point of Landau-Ginzburg potential. So you can move this U0 to the other side, and then you introduce this delta, Kronecker delta, and then you can introduce this series, this function for the Landau-Ginzburg potential in this case. So if you take derivative in V and setting it to 0, then you exactly get this string equation. So the string equation is just the equation for this Landau-Ginzburg potential in this setting. And then using this equation, you get U0, and you have a hope to express everything in terms of U0. Okay, so let me say something more and make comparison with Wilson's renormalization idea. So the space with all these linear coordinates, all these coupling constant, is called the big phase space of the Gromov-Witten series of points. The free energy each genus is just a formal power series in Tn, which mathematically hard to handle. We have to ignore the question of analyticity when we consider this formal power series. So actually, I think this situation is similar to Wilson's renormalization theory. He considered the models with all possible coupling constants. He considered all of them, and then he formed an infinite dimensional space of models. And on this space, there is something called the renormalization flow, which modifies the coupling constant. So those parameters will be called the running parameters because they can be modified by the renormalization flow. And the fixed points of the flow are the critical points. So the situation is similar. And here, I think that's probably the motivation behind Digraph and Witten's work. So actually, then we can consider the mean field theory of a Gromov-Witten theory of a point. So we propose to understand this as an infinite dimensional Morse series. So I think that there should be a Morse function on Wilson space of models. And the critical points of the Wilson space should be just the critical point of this Morse function. And furthermore, that actually there should be some naturally defined metric on Wilson space, so that the renormalization flow is just the gradient flow of the Moore function. So in mathematics, there is this famous or important Moore theory. I think the renormalization theory of Wilson is actually to be understood as an infinite dimensional version of this thing. So furthermore, this naturally defined metric should be some kind of information metric. It should be defined using the hashing of the entropy function. So we can define the free energy, and we should also be able to define entropy. And then we can use some kind of metric there. And then you can use the metric to define the gradient flow. So most of these are actually conjectural at this moment, but the analogy is very clear. We can manifest. So let me move on. So for the Gromov-Witten theory, one can actually associate each point on a big phase with a formal power series. So you take all the coupling constant, and then you can form a series. I add a term with degree 0 here at t minus 1. And then if you take its derivative equal to 0, and then you get a string equation. And then the solution will be denoted by I0. So that's some convention. So then we can actually expand this Landau Ginzburg potential around the critical point. The expansion actually will introduce certain coefficients IM and I minus 1. And IN can be explicitly written down, and I made a typo here, written certain typo here, that there should be a P factorial and so on. So the N here should be of each end P. So they were introduced by Jian Zhou and studied by Iguchi, Yamada, Yang, and my student Qin Zhang and myself. So the INs are formal power series actually in P. I interpret them as renormalized coupling constant. So originally coupling constant are Tn, and you renormalize them into In on a big phase space. So it's a coordinate change. You change the coordinates from Tn to In. And then the first thing that one can do is just to change everything into this new coordinate and see whether you can get something nice or something simple. It turns out that if you change this into the I coordinates, then actually you can get closed formula for everything. So for the free energy in genus 0, you get something very, very simple. Just something like this. And for free energy in genus 2, it's also very simple. It involves only I1. And in higher genus, there is no I0 involved, only something like this. And actually, this expression is a polynomial expression. It's a polynomial. It has only finite many terms because of this degree constraint there. So originally, you get something which is infinite expression. But now, after the change of variable, you get something which is finite expression. It's something that I think it's totally unexpected. The Dabar-Dirac was conjectured originally by Jian Zhou and proved by Iguchi, Yamada, Yang, and myself. The proof, they use a different way to prove it. My method is to consider the so-called change of variable and with a thorough constraint. So using the explicit expression for the IN, we can compute the Jacobian matrix of the coordinate change. And then we change the Virasoro operator. The first operator is the puncture operator. The puncture operator can be exchanged. We can convert that into the I coordinates. And similarly, we can convert this dilaton operator into the I coordinates. Unfortunately, I should put it on the next page. But anyway, just using these two simple things, we can prove that. And furthermore, we need to compute the correlation functions, the endpoint functions. And in Gromov-Witten theory, there is something called the loop operator. So the loop operator is also given by something like the coupling constant and the sequence. So you apply these loop operators on the free energy, then you get, if you apply it once, you get a 1-point function. If you apply it twice, you get 2-point function. If you apply it n times, you get n-point function. So similarly, I change that into the I coordinates, and we can get a simple explicit expression. And then we can apply that n times on the free energy. And then the result is very nice, very simple. It turns out that it's a weighted homogeneous polynomial. So you modify that by something here, and then it becomes a weighted homogeneous polynomial in x1 to xn. So these guys are just defined. So originally you get infinite expressions, but now you always get a finite polynomial expression. So you can use computer to do the job. It's very simple and nice computation. And for example, for the genus 1 free energy, so we can just using that loop operator apply that on this, and you can get very explicit finite expressions. You can get 1-point function, 2-point function, and so on. So in potential theory, it's important to compute correlation functions. Okay, so what is so special about these expressions? As I mentioned earlier, originally all these things are formal power series. So you cannot just discuss anything about analytic properties or closed expressions. That is not expected. So since they are formal power series, we also you look at the convergence. It's hard to think about their convergence. So we expect them to be just make sense only near the origin of the big phase space, where all the coupling constants are 0. So you actually have a big space, but you can actually just stay here if you just say using this formal power series thing. And now, if you change the coordinates, it turns out that the expression makes sense whenever I1 is not 1. So you can move away from this thing to other places. And that is important. So otherwise, you just get a formal thing which has to be confined at 1 point. So the free energy and the correlation can be defined on a much larger portion of the big phase space, and then we can see something called phase transition and other things. So let's move on to that. So the next, let's look at this. In the physics literature, there is something called the market critical points and phase transition. So you look at the Landau-Ginzburg potential. And you look, if the first derivative and the second derivative higher derivatives are 0, and when you hit some place where the derivative is not 0, then what you get is about a market critical point. So you can just take I1 up to IN, IN minus 1 to be 0, and the next one to be 0, and all the others set them to be 0. And then you get the market critical point in this theory. They actually correspond to the minimum model. P to minimum model is coupled to the topological variety. P has to be an integer. So these models were originally discovered in statistical physics, in lattice models, I think by some Soviet physicists, Belavon, Kolyatov, and some other people. And later on, they were studied also. The coupling with topological variety are also studied. So now you start from this Witten conservation, and this thing is actually the 2-1 sorry, maybe that's type 1, 2. And then you move on to the next one, and then move on to the next one. So this is called pure gravity, and this is called Yang-Li edge singularity, and you can go on. So and you can also take this p to infinity. And you go to certain point called the JT gravity. So JT gravity is in a limit picture. P is the odd number, not conventionally they call PQ minimum model. So P and Q are co-prime, not prime. So you can start with the Witten consider original thing, and you consider phase transition, and you can get many other models, and you can reach JT gravity and other places. So let's just go on. So the 3-2 minimum model coupled with topological gravity is called the pure gravity because in the physics literature, because it has central charge 0. The central charge is actually a dimension of certain fictitious space in which there is a geometrical approach called the Liouville quantity theory. So the dimension is 0, that means there is no space. And the Witten considered a central charge -2, so it's a fictitious dimension of -2. So what one can do is just to change the variable from T1 to T1 plus 1. So we shift. So we shift to here, yes, T1 equals to 1. So all these guys lie on this hypersurface. So you shift there, and then you also change this to this arbitrary 2A. And then you can do the computation, and then you see the fractional thing appearing. So the fractional, you get T0 to the T0 to the half power. And then you can compute using the expression that I got earlier, and you can explicitly compute, and you see that fractional thing again and again. And also you can use just the I coordinates, and you plug it in, and then you get expressions. This method actually got matches. This result matches the result obtained by Bergery, Anna, and Iwaki and Sanchez by topological recursion. You can start with some spectral curve and perform topological recursion. Actually, they got the same results. And here is just say we can consider another example, just the 5-2 model. They arise as the Yang-Li, this should be as the Yang-Li edge singularity. Similarly, you move from here to the hyperplane where T1 equals 1, and then you can do, and this time you see some fractional power. The power is 1/3, and then you get similar result, but easily computed using the I coordinates. And again, you can compute their endpoint functions. So in general, you can look at the case critical point, and you can use the expressions in the I coordinates to obtain the general asymptotic behavior, and you get the fractional power. So the fractions here are called critical exponents. And also for the endpoint function, there are some predictions in the physics literature called the TDK formula, Davi, Distler, and Kawai. So they studied these things from the point of view of Liouville quantum gravity, and they derived certain formulas for the fractions. So these fractions actually matches with the prediction for the PQ minimum model. So what I trying to say is that you can starting with Witten's topological gravity, and then you can consider phase transition and get this model. And then you can go on to consider Witten's R spin intersection numbers. Then you can get all these PQ minimum models. Okay, so let me summarize this. Summarize this thing for the moment. So actually, I have mentioned the following things from statistical physics: mean field theory, order parameter, lambda density theory, phase transition, and critical exponent, Wilson's renormalization theory, and emergent phenomena. So far, I have covered the first three. And what about the emergent phenomena? What actually also emerged in this picture? So that's what I'm going to explain next. Okay, so let me recall what Witten conjecture conservative theorem is about. So this most remarkable result on the Gromov-Witten theory of a point is the following conjecture written first proved by Kontsevich. I think that there are many other proofs, including many proofs given by Professor Liu in the audience. So the first statement is that the partition function is a tau function of the KDV hierarchy. And the second statement is that it's uniquely determined by a sequence of referral constraints. So what does that mean? It means that the specific heat in this theory here are including all the spin coupling constants. And this is so-called a genus expansion. I consider the genus G part of the free energy, and then I introduce lambda G here. Sorry, lambda here. And then you satisfy the KDV hierarchy, which is a sequence of differential equations. And on the right-hand side is recursively defined by the linear recursion relation. So these are the so-called Gelfand differential polynomials. And the Virasoro constraint tells us that there are certain differential operators acting on the partition function will give us 0. And actually, this completely determine this partition function. Okay, actually, I have developed two other methods to compute the endpoint function correlated, the endpoint correlated of the Gromov-Witten series of a point. So the first approach is just say we consider a more general situation of the KT hierarchy. I derived some formula of this form. This formula depends on a certain kernel. This kernel can be explicitly written down using the array function AI and BI. I will not go into the details into this, but something like this actually, something similar to this has already appeared in the literature of matrix models. They have something similar. So actually, I have also considered what is their relationship. Another thing is that we can secondly we can use NRN topological recursion. It just says the endpoint function can be computed using the NRN topological recursion. So let me explain what that is. It depends on two inputs. The first input is a curve called a spectral curve. Usually it's a rational curve with some kind of parametrization. So it's X and Y. So they are certain, they lie on a plane, XY plane, and these are specified by this parametrization. And the second input is the so-called Bergman kernel. And in this case, the rational curve is take the simplest, that's the Bergman kernel is given by this. And then you look at the spectral curve and assume that the spectral curve has only one branch point. That means just X is a Morse function in Z. And then you can expand this X in terms of something called local area coordinates, and also you expand the Y. You expand that into the local area coordinates, and you can define something called the recursion kernel K here, using the Bergman kernel, and also this there is an involution. And then NRN topological recursion is a simple recursion. You just take the relative view, and then here it's just say either you reduce the genus by 1, or you go to correlations with fewer mark points. So it's a recursion that you can perform. So amazingly, in the simplest case, that X equals just a square of the coordinate y equals just this thing, then the result is the correlators defined by the unknown topological recursion actually coincide with the correlator of Witten constraint problem. So this topological recursion actually gives us all information about the Witten constraint problem. So in other words, all the information about the Gromov-Witten series of a point is actually encoded in a single, very simple algebraic curve like this. So what does that mean? So where does this thing come from? We need some kind of interpretation, and I interpret this as an emergent phenomenon. So this is very strange, and I think probably the emergent phenomena in statistical physics is actually useful to understand this. So something related is to reformulate the Virasoro constraint, the digraph Valinda constraint is considered a field of operators. So these betas are operators, bosonic operators, taking derivatives with respect to TK and also multiply these things like this. There are some funny coefficients here, which is there are some certain interpretations, but what one can say is that if you take the square of this field, and the negative means take the part with negative powers only, and then you let it act on the Witten constraint self function, then it gets 0. So that is just with a thorough constraint reformulated this form. And then we can also consider the genus 0 part. The genus 0 part just take the genus 0 part of the free energy, and then what you get is this. Then the genus 0 part of the Virasoro constraint is just this thing. And then by taking all Tn to 0, what we actually get are just some generic curve. So what I mean is that you take y square equals something which is positive in x, and then that equation is just the spectral curve. And then what you can do is that you take these special coordinates. That means you move from this thing to other points. Then you get some different curves. So these guys actually is obtained by taking the genus 0 one-point function. So what I want to say is that the genus 0 one-point function determines the spectral curve of each of these models. And also you can take the genus 0 two-point function that determines actually the Bergman curve. So it turns out that the Virasoro constraint in this case is equivalent to this unordered topological recursion. So I just say that the unordered topology in this case is just an emergent phenomenon. You go to this infinite degree of freedom, and then something pop out, emerges. So not only do you have this spectral curve, you also have this topology recursion. It determines this completely. It actually can be done more generally. So the KTU hierarchy can be embedded into the KT hierarchy, which is a bigger things. And then you can consider the so-called wave function. This should be just one equality here, and then the wave function can be written as you have action here. So this is just a WKB expansion. So the action actually for the wave function, for the top function of the wave function, we can actually write down something similar. So that actually returns. That is almost the same with what we have on the previous side. So let's see how much time do I have. Good 20 minutes. Okay. So probably I can go a little bit slower. So let me summarize what I have explained so far. The emergence of the NRN topological version in Gromov-Witten series actually involves genus 0 1-point function and genus 0 2-point function. I have only talked about Gromov-Witten series for a point, but actually it's more general. I just use it as an example to illustrate the ideas. In this case, the Virasoro constraints are equivalent to the reconstruction of the whole series from this data by this topological recursion. So far, statistical physics has shed some light on this thing. So this is emergent, and the question is like, can you go backwards? Can you use such insight to say something about statistical physics? So I have borrowed ideas from statistical physics, and next I want to go the other direction. So the statistical physics is a very big field, so I only focus on small things that I can understand a little bit. So that is the fractional quantum Hall effect and the interpolating statistics. So in the 1980s, the discovery of quantum Hall effect and the fractional quantum Hall effect actually led to many new progresses in statistical physics. And actually, many people won Nobel Prizes in physics on this subject. And one of these Nobel winners, Hoden, actually introduced the notion of fractional statistics. This notion leads to the notion of interpolating statistics. So what I mean, these are statistics that are interpolating between Boson, Einstein, and Fermi-Dirac statistics. So let me explain what I mean by that. So for a system of m identical particles, each of which can occupy small n states corresponding to different energy levels, E1 up to En, the canonical eigenfunction has the following structure. So we assume that they have this structure. They are just given by summation of this Ni, this equal to N. So the total total number of particles is capital N, and these WNIs are just the number of particles at energy level EI for each of these I. So these are just given by the Boltzmann rate. So this assumption actually means that there is no interaction between the particles at different energy levels. And then what one can do is that you can somehow just consider the one particle partition function, which is just the generating function of this Wn. And mu here is the so-called chemical potential. These were done in statistical physics. And for example, there are three kinds of very famous statistical physics that have been used in statistical physics. The first is the Boson-Fermi, the Boson-Einstein. And this is the Fermi-Dirac, and this is the Boltzmann chips. So they're given by different generating functions. And then we can, using statistical physics, to consider the so-called mean number of particles. So these are actually given by taking the logarithm of this thing. And then for the Boson-Einstein, Maxwell, Boltzmann, and Fermi-Dirac, they're actually given by these things. So if we plug in this x back in here, then we get the original familiar expressions in the textbook of statistical physics, statistical mechanics. So these are very familiar. And then you can take the logarithm, and then the logarithm, you can also consider the expansion of the coefficients here are called cluster coefficients. I'm just using following things practiced in statistical mechanics. We can also define the entropy. So the entropy of this thing you can define by the Legendre transform of the free energy. So that's the free energy minus log x, and also take the derivative of f of x with respect to log of x. And then you can also invert x and w and x, w in x and x in w. And then what one can get is just some expressions in either x or in w. So in the case of a Boltzmann chips, the entropy is just the standard entropy. And for the Boltzmann, for the Boson-Einstein, the entropy is some kind of a new kind of entropy. And for the Fermi-Dirac, you get another kind of entropy. And one see that what the difference is that you can change the negative sign here to plus sign here. So you can get different kind of entropies, and you can get different kind of statistics. And then because we were dealing with this so-called one particle partition function, so motivated by Gromov-Witten theory, we define also this case the spectral curve associated to these interpolating statistics. So we can actually define them in two different ways. One of them is just say z equals z of x. The other is that I introduce some variable z equals exponential y. And this will be called spectral curve associated with the corresponding statistical interpolating statistics. So why do I want to do that? So I want to answer the question. So the question is it possible that such spectral curves actually coincide with the spectral curve of Gromov-Witten theory of some target space? Favorably, some Calabi-Yau threefold. Is that possible that Calabi-Yau threefold and Gromov-Witten theory can say something about fractional quantum Fourier effects here? So I want to propose something which probably is nonsense, which is related quantum Fourier effect to string series. Then, surprisingly, I found that there is some combinatorial tool called the Ombro calculus. It's a very useful tool to study the interpolating statics. Ombro calculus is a symbolic method used by mathematicians in the 19th century to magically prove with quotation mark some combinatorial identities. They were not believed to be rigorous originally, but since the 1960s, Rota and his collaborators have constructed a rigorous mathematical foundation for such things based on the language of linear functionals, linear operators, and their adjoint operators. So this looks very much like quantum mechanics. So it turns out actually it can be interpreted in terms of quantum mechanics and coherent space. So Ombro calculus actually is a combinatorial thing, but it can be somehow interpreted in terms of coherent space. So Ombro calculus show that the occupation numbers of interpolating statistics are related to the so-called binomial sequence of polynomials in combinatorics. So in the following, I just want to mention certain examples which give us something interesting. So in 1826, Abel generalized the binomial identity by changing this x to the k, y to the n minus k to something like this. This leads to certain interpolating statistics with free energy, which I call F Abel. That's the free energy associated to this thing, which is a series. And this series is the so-called Lambert series. They appear in the study of Katie of counting trees. So tree diagrams is just a general zero thing. And then you can also invert this thing. You can get, you can get a W. And the spectral curve in this setting, you can find it explicitly using something called the Lagrange inversion formula. You get something like this. And this actually is this spectral curve of this one actually exactly the spectral curve in the study of invariant topological recursion of Hewitt's numbers. And its generalization is called modified or generalized Hewitt's number. So this kind of things actually the spectral curve appears in a string theory or literature. And if we go on to something more complicated. That is called the gold polynomials. So these are the sequence of polynomials with two parameters. So the Abel has only one parameter. Here we have two. And then you get this W, and you can also invert this thing to get X in terms of W. And then actually, if you look into the literature of interpolating or fractional statistics, and then you find that there's a physicist called Wu Yongshi. He has a formula generalizing Houdan statistics. So this is called the Houdan-Wu statistics. So if you take something here, you can actually you can make it exactly. You can recover the Houdan-Wu thing. So you then you can consider the spectral curve here. What is behind the spectral curve? The spectral curve can be using, again, the Lagrange inversion formula, and you can get a curve which is complicated. It has two parameters. You can take some of these parameters to some special cases. And then if you go to 0, then what you get is just the Abel thing. But if you take this choice, then what you get is something called the spectral curve for the fringe topological vortex. So the topological vortex was used in studying the local mirror symmetry, the local Gromov-Witten invariance of C3, of poly-Calabi-Yau threefold. And something like this actually pop out also in this setting. It also, you can take some other choices, and you can the so-called Kaplan curve. In the literature, there are many problems which are somehow related to the Kaplan. To the Kaplan. So where is the Calabi-Yau threefold? I'm considering only a curve. Where is the Calabi-Yau threefold? You introduce two more variables, and then this is Calabi-Yau threefold. And then period integrals can be reduced to this thing. So this is the analogous institution with digraph. Then Marinois. So on this side, we're doing just some curve, but you can also relate it to Calabi-Yau threefold, and that you can. That's you do B series on this kind of Calabi-Yau threefold. It's equivalent to do topological recursion on a spectral curve. But where do we get these things? We get this from fractional quantum Hall effect. So the crazy proposal is that possible that Calabi-Yau threefold can be used to somehow say something more about what is going on in the statistical physics of fractional quantum Hall effect. So let me make a summary here. The statistics interpolating the Bose-Einstein and Fermi-Dirac statistics are actually determined by their one-particle partition functions. The logarithm of this partition function is the analog of genus 0 one-point function in Gromov-Witten series. So we can define the spectral curves in a similar fashion. The Wong-Bro calculus in standard and combinatorics actually provides many examples of such things. And then they are one of the examples, special examples actually are related to Gromov-Witten series of friends, encoded in the friend topological vortex. So the question is that possible? Can we actually use the mirror curve of Calabi-Yau threefold to provide more examples, more interesting examples of interpolating statistics? And a further question is, can we use this higher genus Gromov-Witten invariants of this Calabi-Yau threefold to say more about statistical physics to systems satisfying such interpolating statistics? Okay, I will stop here. Thank you very much for listening.
Thanks for your talk. Is there any generalization of this theory to non-abelian fractional quantum Hall effect where the spin is replaced by a higher dimensional representation of the braid group?
That I don't know. There are different ways to study these things, either by this, monotony of braiding relations, or by this. I'm taking an approach of interpolating statistics, but I'm not sure that these two kind of approaches are related or somehow equivalent to each other. That I don't know.
Okay, thanks.
Any questions? Okay.
Hi, Professor. I have more of a not question that's not related directly to the topic. I want to ask, what's your speculation about this theory being used in the further development of topology relating to physics and statistics?
So I'm not sure that I understand your question. So you want to say, so let me just say something, and then you maybe that answer or maybe not. So I'm thinking that maybe Calabi-Yau threefolds can be used to study probability theory. So we have space of probability distribution, which is a very large space. And then probably one can associate a Calabi-Yau threefold to each one of them. And then you can probably do something similar here. And in probability theory, you only have something which is a leading order, which is genus 0. But in Gromov-Witten theory, you always have higher genera and multi-point correlation functions and all those things. So the geometric theory is more interesting. It has higher order things. But in probability theory, I think mostly you get genus 0 contributions. So I want to convert something in probability theory into something in geometry in Calabi-Yau threefold and in Gromov-Witten theory, and then we can say something more, hopefully.
Okay, thank you. That was very helpful.
Here you are talking about when P goes to infinity, then we have a GT gravity.
Yes.
This reminds me that is this related to ADS-FT? Because usually when people considering the holographic duality, people consider the large elements, then we have some gravity dual appear. And here we have a family of the statistical mechanical model. When we take this limit, we have emerged gravity. We have a gravity theory.
I think I have an answer which may not be correct, but let me just say it's mention it anyway. I think there is a even larger space, and ADS-CFT is taking limit in that larger space. I'm taking limit in a smaller space, which is topological gravity. But you go to certain bigger space of series, and then inside that space you take certain limits. That's ADS. I'm just taking limit in a smaller space, which is more familiar to me, which I can handle. But certainly, you can think of that there's very high dimensional space, but I'm just living here. Probably you are here, but the limits. So you're taking limits in other directions. Probably not from on this slide.
If no more questions, let's thank Professor Zhou Jian again.